So we'll meet on Thursday, and then we'll meet next Monday. So on Thursday will be our last lecture with new material. And next Monday, I'll go through some old examination, written exams. They're also available through the web page. You can download some of them and take a look. I haven't completely decided on the format of the final exam, but it will include the written part and the oral part, as everything nowadays does. But well, the examination is still in mid-January, so you definitely will have some time to prepare. Okay, this, I guess, is it of general things. It says on the web page that the next time would be self-study, but this is from the previous version from the last year. I'll give a regular lecture on Thursday. Okay, let's see. Now let me share the screen. So today we'll continue discussing optimization in graphs. Yeah, and so the thing we did last time, just me recall a little bit briefly. What we did last time, we were discussing two problems. First one is that if we have a weighted graph, and the weighted graph is an undirected or directed graph, such that its edges have positive weights. Well, meaning something, I don't know, capacity, resistance. Well, that's a usual situation. And we discussed two questions. The first one was how, if we fix one vertex node, how to find the shortest distance from this node to the remaining vertices, meaning if we connect it by a directed or undirected path, depending on the situation, what would be the minimal sum of weights of edges in this path. And this was done by a certain algorithm. There is no kind of answer in the closed form in some kind of a formula, but there is a simple algorithm how to do this. And this is due to Dijkstra and Kroshkar, maybe was the other guy. And it's not very complicated. You start, you first take your vertex from which you measure your distance to the set of considered vertices, and you label the distance from this vertex to itself as 0 and to the remaining vertices as infinity. And now you are successively changing the labels of the rest of the vertices by checking whether there is a shorter path, the path with a shorter total length than those labels you have at the moment, and you consider this procedure. And every time you finish a certain step of your algorithm, you check which of the newer vertices which were not in your original, which in your current set of vertices, have the minimal new length of the path. And then you take this vertex and merge it with and put it in the set of already considered vertices. Now, the second question we discussed was about minimal spanning trees. So any connected graph has a minimal, has a spanning tree. And now the question, and many of them, and the question was how to find such a tree which has a minimal total weight if you are in a directed situation. And there were two versions of the algorithm, one based on the edges and another one based on the vertices, and both are very straightforward. The one which with edges, you just pick each time the wedge with a minimal weight such that if you add it to your collection of edges, you'll not form a cycle. So if you have an undirected graph, you just start with an edge of a minimal weight. If there are several of them, you just pick any of them. And okay, this is this guy we have taken. Then we're looking at other edges, and again choosing a minimal edge such that if we add it to our collection, we're not getting a cycle. And if you continue in this way, you get a tree of minimal spanning tree. Or the other way is you start with a graph and you pick at random some vertex. And now we're taking the edge of the minimal length, connecting this vertex to the rest of the world. And now you're adding to your set of vertices the end of this edge you have chosen. And now you have now two vertices. You're looking what is the edge of the minimal weight which connect these two vertices with the rest. You add this second end of this edge to your group, and so on and so on. And then at the end, once you have once you have visited all the vertices, you are done, and you have a minimal spanning tree. Okay, that's what we did last time. Now let me move to what we'll be talking about today. Oops. Good. So we'll be discussing, I think it's section 13.3, maybe 13.3, I think. It's about transport networks. It's a very interesting and important and fairly easy to understand sub-area in graph theory, which was a big success in the 70s, I think, late 60s. So again, what is a transport? Transport network is a weighted graph, usually directed weighted graph, such that the weights of its edges are positive integers. So let me write this down. And you can usually approximate any weighted graph by transport network. So, but it's from the algorithmic point of view, it's usually much better to consider positive integer weights and just any real numbers. Okay, transport network is a connected directed graph. I have, yes, so there is one more property that I have to add. With a function, with a weight function, call it C, from the set of vertices across the set of vertices to the positive integers, such that so first of all, so there exists a unique vertex with incoming degree 0. So this is called the source of the network. The source means that all edges are directed outside. Sorry. Jag har lektioner, kan inte prata. Om en timme. Hej. So this is called the source.
Just a question what you wrote. So exists a unique vertex with, I don't see the word there.
With incoming degree.
Incoming, thank you.
Incoming degree vanishing. So that's a kind of picture we get. All vertices are directed out. Okay, so then there exists a unique vertex with outcoming degree equal to 0. This is called the sink of the network. That means that all edges are directed towards. So this is the source, and this is the sink. So water comes out of here and water goes down into the sink. Okay, and so the weights are, the weight C in this area called the capacity of the edge is a non-negative integer. And it can be positive only on the existing edges of the graph, of course. So if for a non-edge, the capacity should automatically be 0. So let me draw a simple example for you. And we'll use this example further. So the source is denoted by A in my picture, and the sink would be Z. Okay, so here is my example. We have the following graph, directed graph. Okay, so this is my source. This would be my sink. And then I have further vertices B, D, G, and H. And let me put my capacities 5, again 5 here, 6, 5, 7, 7, 2, and finally this would be 6. Okay, so this is a transport network. So these are usually used as models to communication channel, or in logistics situation, transport networks, and the capacities usually mean some limited resource. I don't know, what could it be? I don't know. The width of the road, how many cars can pass a certain road, and so on and so on. And I don't know. So in the Wi-Fi situation, what's the maximal number of megabytes you can get in a second, and so on and so on. So that's pretty straightforward situation. One can model with this kind of things. And now, what is a network? What is a flow in a network? So given a network, say capital N, which consists of a graph and this capacity function C, with the source A and the sink Z, we say that a function f for flow from the set of edges of our graph to, again, non-negative integers is a flow if it satisfies the following two basic conditions. So first of all, the flow for all edges in the set of all of the set of edges, we have that the flow through this edge is at most the capacity of this edge. We cannot exceed the capacity. We cannot put more water in a small tube. Okay. And then for any vertex V, which is not the sink and not the source, we should have that the amount of flow coming in should be equal to the amount of flow coming out. So we get the following equality, that for all vertices W in V, if we look at the flow from W to V, so this is the incoming flow, should be equal to the flow which leaves. Flow from V, so I don't know, so maybe I will use U here not to confuse you. So outgoing, outgoing flow. Okay, so the amount of water coming in, or the number of cars coming in at every vertex of any crossing, any crossing should be equal to the amount of cars leaving, to the number of cars leaving this thing, of course, except for the source, where you can think of as the source of your water, as your well, and then you have a sink, another one other vertex where everything can disappear. Say I don't know, you have a bus station from where your buses come, and then you have another place where they should collect at the end of the day. Okay, now here is an example of an actual flow related to the graph which I had before. Example of a flow. In the graph we had before. So the graph looked like this, but I'll put different numbers on the edges, which would be smaller than the capacities of the edges, and they will satisfy this balancing condition at all vertices except for the sink and the source. Okay, so we can put 5 here, we can put 6 here, we can put 4 here, 5, 6, 5, 2, and I guess and 1 here, and I guess this is it. Yes, and we see, so from here, so we have the total 11. So from A, flow from A equals 5 plus 6, which is 11. Oops, I forgot to put 1 here on this one. Okay, now we see that we have the balancing condition at all other vertices except for Z. So flow towards Z also equals 11, and we'll prove a result about this soon. So the outgoing flow from A is 11, the incoming flow to Z is 11, and all other vertices, the flow should be 0. So for example, if we look at this vertex, we have 6 is coming in and 6, 5, 1 plus 5 is coming out 0. So if we look at this thing, 5 is coming, so 6 is coming in, 5 plus 1 is coming in, 4 plus 2 is coming out. Here, for example, we have 4 plus 1 coming in, 5 coming out, and here we have 5 plus 2 coming in, and 1 plus 6 coming out. So at all other vertices except for sink and the source, the total inflow, the inflow equals the outflow. This is the condition on the flow. Okay. Now, so our optimization problem would be as follows. So given a traffic network, a transport network with its restrictions on the capacity, we want to maximize the total flow which we can put through this through this network from the source to the sink. This is, so we're given this directed graph with one source and one sink and positive integer weights, and we want to know what is the maximal flow we can achieve in such a network. So let me put this problem. Given a network, transport network, what is the maximal flow? I have to define what we mean by that, but it's fairly obvious. Flow we can achieve and how. I want to define formally what is the value of the flow. So the value of the flow is the total definition. So the value of the flow is the flow F in a network G C is by definition the sum over all vertices in V of the graph F of A to V. So what is, we know that A is the source. There are no incoming edges. So all edges are outcoming, and we're counting what is the total outflow from the source. So total outflow from the source. Fairly natural notion. Okay. And we'll have a lemma which will allow us to calculate the same thing, the value of the flow, using both the sink and, in fact, all other so-called cuts in a graph. So if we have a flow which satisfies this balancing condition at all vertices except for the source and the sink, there are many ways to calculate the same number value of the flow. Okay, so in our example here, the outflow, or the value of the flow is 11. So that's the total thing leaving A, 5 plus 6. Okay, now we have to define a cut. So a cut of a directed graph G is just a decomposition of its set of vertices into two groups. Is a decomposition V of G equals two disjoint sets P disjoint with P complement. So the disjoint union. So just any, we take one subset of vertices and the rest of the vertices would go to P complement. Now, if we have a net, then we want for a transport network, we want A to be contained in P, and Z, the sink, to be contained in its complement. So we're just decomposing our vertices in two disjoint sets, and one is containing the source, another one is containing the sink. This is it. This is all what the cut is. Okay. Now we have a simple lemma now, allowing us to calculate the value of the flow using any cut at all. Okay, lemma. So if n, which is a graph, plus this capacity function C is a network, and P complement is any cut of n, then we can calculate the value of, and F is a flow, sorry, and F is any flow on n. Then we have the following relation, that the value of this flow, which is the total outflow from the source, equals the sum of all flows. So if we take V in P and W in P complement, and we look at the flow from a V, yes, okay, so from V to W minus the flow from W to V. So in principle, for a directed graph, it might happen. Okay, so we have directed edges. If an edge is directed from V to W, then we take the value of the flow on this edge with a plus. And if it's directed the other way around from P complement to V, then we take its value with a minus sign. Okay. For example, if we look here on my example of the flow and take the following cut like this. So we separate these three vertices. This would be my P, and this would be my P complement. Yeah. So we have edges only going from P to P complement in this situation. So we have take all of them with a plus sign. So we get 4 plus 2 plus 5, which is 11. And you see that's the same number we got from just looking at A and taking the outflow from A. And the decomposition of P equals A and the rest of the vertices belonging to P complement is one of the possible cuts, of course. And the value of this cut is exactly the definition of the value of the flow. Yeah. But I'm saying in this lemma that it doesn't matter actually which cut you take, as soon as P contains A and P complement contains Z. So you can calculate the value of the flow by taking what flows from P to P complement with a plus and what flows backwards with a minus sign. You'll get exactly the same number. Okay, and what is the proof of this thing? And the proof is as follows. So by definition, the value of the flow by definition is the sum of all vertices in V, f of A to V. So we're taking everything which goes from A to all other vertices in V. So since we can rewrite this by even adding, since the incoming degree of A is 0, so we can formally add this thing with a minus sign because it's actually 0, and this doesn't change anything in our consideration. And now let me add to this thing a bunch of other entries which are the sum which is 0, but it will allow us to regroup our terms and get the result which we want. So we're adding the summation over W in P and W which are not our source vertex of summation f of W V minus f of VW over V in E. And this is because of balancing condition. This is 0, so we can add this thing. Now we can, here we're taking all vertices in P which are not A, and here we're taking A itself. So we can add these two things together, and we're getting the summation of all W in P, including A now, summation over all V in V of f of WV minus f of VW. Okay, and now we can regroup it in a different way. So summation over all W in P, V in P, plus summation over all W in P and V in P complement of f of VW, f of WV, sorry. And so this is one sum, and now we have similar with a minus sign, summation over V in P, W in P, sorry, V in P, and plus the summation over W in P and W in V in P complement of F going the other way around. Okay, now we see the two pieces cancel each other. So these two guys cancel each other, and what is left would be the summation over W in P and V in P complement of f of WV minus the other way around, f of V in W. And that's exactly the formula which we wanted to show from the beginning. Okay. Now, in particular, we have the following corollary, small corollary of this thing, that again, under the above assumptions, So the value of the flow equals the total inflow to the sink. So this is incoming flow to the sink. Okay, there are several ways to show this. In particular, we can just take as a cut P complement equals to Z, and P equals to all vertices except for Z. And you'll get exactly this situation. So we have a general lemma for any cut, but in the case of this specific cut, which consists of P complement being Z and P equal the rest of it, we'll be getting exactly this formula. And we can again look at our picture and see that the outcoming flow from A, which is 11, 5 plus 6, equals the incoming flow to Z, which is again 5 plus 6 in this situation. But actually, again, if you have any cut separating A from Z, and you can count the number of the total inflow from P to P complement minus the flow back, you're getting the same value. Okay. Yeah. Now we have to move further to the formulation of our main theorem. For this, we'll need one more definition of a capacity of a cut, and then we, after one small lemma, will be able to formulate our main result for today. Sorry. So let P complement be a cut. Oops, sorry. Be a cut of a transport network N consisting of the graph G and the capacity function C. Now the capacity of this cut is by definition the following thing. It's the sum of the capacities of all edges from P to P complement. Oops, V to double. So once we have a cut, we're looking at all edges going from P to P complement, not the other way around, directed that way from V is in P and W is in P complement, and adding out and adding up all their capacities. That's the capacity of the cut. For example, if we go back to our picture here, the first picture, yes, this was our transport network. If we're making such a cut, yeah, so this is P and this is P complement. Its capacity of this cut is 5 plus 6 plus 7, which is 18 in such a situation. Good. Okay. Yeah. Now, so let us prove a following simple lemma. So given a network N, which is GC, a flow F, on n, and the cut p complement. One has the following inequality, that how do we call this? The value of the flow is smaller or equal than the capacity of the cut for any flow and any cut. So the value of the flow can never exceed the capacity of any possible cut which separates the source from the sink. And the proof is very easy here. And after that, we'll be able to formulate our main result. Okay, so the value of the flow is by definition what? Or no, by our lemma. So by definition is the total outflow from the source. But we also learned that for any cut, the value of the flow is the total outflow from P minus the inflow from P to P complement minus the other way around. So we have, it would be the sum over all V in P and all W in P complement of the flow from V to W minus the other way around. Okay, so this is obviously, this is negative contribution, so we can estimate it from above by just throwing it away. So if we just count what flows from P to P complement, this would be at least as much. Now, each such guy is bounded by the capacity of the corresponding edge, yes, so this would be smaller or equal than the capacity of the edge from V to W. And this is, again, by definition, the capacity of the cut. So the capacity of the cut, P complement. Okay, now we're done here. So we have these fundamental inequalities, so that for any network, any flow, any cut, the value of the flow is bounded from above by the capacity of the cut. And now we're ready to formulate our main result for today, and I'll be making a break after that. So main theorem, which is due to two Americans, Ford and Fulkerson, max flow mean cut theorem. And I guess you can guess what it says. So for a transport network, the maximal value of the flow equals the minimal capacity among its cuts. So if we're given a transport network, we should look at all possible cuts, calculate their capacity, which is the total capacity of edges going from P to P complement, and take their minimum. This minimum, obviously, by the previous lemma, should bound the flow, but this result says that it actually equals to the maximum. This minimum equals to the maximal possible flow through the network. Okay, so let me make a break, maybe 10 minutes now, and we'll continue soon. Back. now. So I hope you're listening. Now, the last thing for today, I'll be trying to explain how this maximal cut, minimal flow, the other way around, maximal flow, minimal cut result is proven. Let me repeat what it says. It says that if we have a transport network N, which consists of the directed graph G with a capacity function C, it is connected with just one source, one vertex where all edges are coming out, and one sink, one vertex where all edges are coming in. And we're looking at the maximal value of the flow. And flow is a function on the edges such that at each vertex, except for the sink and the source, the sum of incoming flow equals the sum of outgoing flow. We have a balancing condition. And at each vertex, its value does not exceed the capacity of this edge. And we define the value of the flow as the total outgoing flow from the source. But then we have shown that the same value can be calculated for any so-called cut. Cut is just a separation of the set of vertices into two groups, one including the source and the other including the sink. And the value is we just count what goes from, they are called P and P complement, what goes from P to P complement minus what goes the other way around from P complement to P. And this in particular will be equal to the outcoming flow from the source and will be equal to the incoming flow to the sink. So you can calculate the value of a given flow in many different ways by taking any possible cut. And we want this number to be maximal possible among all flows. And the theorem says that this maximal value of the flow equals the minimal capacity among all cuts. And for a cut of the form P complement, its value is we take the sum of capacities of all edges going from P to P complement. And this is it. We're not taking into account those which go back from P complement to P. Okay. Yeah. Now, this is the formulation. Now to prove it, we need to define two small things. One is a chain, and the second one is the so-called augmenting path. Okay, and this would be the last two things we need to prove this main theorem. So a chain is just a sequence of vertices.
Are you trying to draw right now? We see your face. Are you trying to show on the
Yeah. Just 1 second. Yeah, sorry. Let me share. Yes. Come on. Good. So this is the main theorem, and now we need a couple of notions. A chain in a directed graph. Is just a sequence, say G, is a sequence of pairwise adjacent vertices, a sequence of adjacent vertices. So V1, V2, and so on, Vk. So Vi and Vi plus 1 are adjacent. So that means that there is either either an edge from vi to vi plus 1 or the other way around, because it's a directed graph. And now we say that E is a forward edge. So if it goes from vi to vi plus 1, so that E is a forward edge, so we go forwards. If it goes from vi to vi plus 1 and backward vi plus 1 and backward edge if it goes backwards. It is vi plus 1 vi. So in other words, so if we're given a graph, so a chain is just a sequence of edges like this. So these are forward, oops, this is forward, and this goes backward, and this goes backward. So if you want, if we forget about orientation, we have the chain in a non-oriented graph. We have a path in a non-oriented graph, and we just want to keep track of whether we go according to the orientation, this is a forward edge, or we go against the orientation, this is a backward edge. Okay, an augmented path in a transport network, and something is wrong. So augmented path, an augmented path, yes. Okay, so we need to specify a flow, of course, for a flow F in a network N consisting of G and capacity function C is, okay, a chain starting at the source A and ending at the sink Z, and such that so f of E, so that two, so if E is an edge in this chain, so f of E should be smaller than the capacity of E for all forward edges. And f of E should be positive for all backward edges. Okay, so if we have a, say, something like this, so this is, say, the source, and this is the sink. So we assume this is called a augmented path if it's a smaller than capacity on all forward edges and positive on all here should be also smaller than capacity. So we should be smaller than capacity. It means that we should still have some you know, some additional size to put an extra flow in this direction. And if we have the edge going backward, it means that we have a positive flow back. That means that if we shut this out, we still will be able to put some additional thing through. That's what the intuition behind this notion is. Okay, for all forward edges, we have to have the flow smaller than the capacity of the edge, and for all backward edges, we still have to have a positive flow back. That's what an augmented path is. And now the next lemma is crucial, and I don't quite understand why it isn't what we need to prove the theorem, why it's not called the proof of the theorem, but that's what is done in your book. So I wonder if I have jumped over a certain lemma, but I probably have to go back to one lemma. Yeah, I think yeah. Okay. So lemma says that so assume that we are in a transport network with a flow such that no augmenting path exists. Then there exists a cut for whose value such that the value of the flow equals to its capacity, and therefore it should be maximal. Because we know by a lemma that the value of any flow is strictly smaller than is small or equal than the capacity of any cut. Yeah, so then they will be getting a maximal cut. Okay, so let n you see be a network, and f be a flow in n such that no augmenting paths. Oh, sorry, what is it that I'm writing? Paths exist. Then the claim is so then there exists a cut P complement such that the value of the flow equals the capacity of this cut, and then the flow is maximal. Before I prove this lemma, I think I forgot one lemma before, which would be used in this one, additional lemma. So we have shown that for any cut, the flow is at most equal the capacity of this cut. Let me now characterize when those things are equal. Okay. So where is this thing? So just a little bit confused. This lemma, just 1 second. Yeah, here it is. I think I missed this one. So given a network and the flow F and the cut P PC, one has the following. The value of the flow equals the capacity of the cut. It's always an inequality, but say we have the inequality if and only if. So the following two things are satisfied. One, so for any E which goes from, so say we have an edge from V to W, and V where V belongs to P and W belongs to P complement. Then we should use its capacity fully. So in this flow, the flow through this edge should be equal to the capacity of this edge. So we should use all capacities over all edges from P to P complement maximally. And if this edge goes the other way around, then the flow should be 0 through this edge. Okay, how do we show that? And that's maybe this lemma, it will explain why we need this notion of augmented path and why is it interesting for us. So here is the proof. Okay, so we know by the previous lemma, so the value of the flow, if we have a given cut, so we can calculate its value by the sum of all V in P, W in P complement, F of VW minus F of WV. Okay, and this is of course small or equal, then we if we remove the second term which comes with the minus sign. Yes, so we have that this is smaller or equal than V goes belongs to P, W belongs to P complement of F of VW, and this is it's small or equal than the capacity of the corresponding edges, and this, which is by definition the capacity of the cut in P and P complement. Now, when do I have that this part equals that part? When does it happen? If we look at these things, we see that it only happens if for all edges going from P to P complement, the flow should be equal to the capacity. Yes. So the equality happens if two conditions are satisfied. So satisfied. So we use F of UV equals F of VW equals C of VW for edges from P to P complement, and we don't allow anything back, and F of edges going back have no flow at all. So if you have an edge going this way, no flow. If you have edging going that way, so you have to use it maximally. So this explains why we need this augmented paths in the proof of the main theorem. Okay, so let's see. So with this additional lemma, now I want to prove my major lemma, which is saying that if we have a network with a flow such that no augmenting paths exist, then there is a cut such that the value of this cut, the capacity of the cut equals the value of the flow, and therefore this flow is maximal. How do we proof of the lemma of the main lemma of the main lemma? Okay, it's a little bit complicated, not too complicated, but still. Okay, let me try to sketch this. So okay, so to create a cut P complement in this situation, we do the following. So look at all chains starting at the source. Now, okay, assume that you have, so P will consist of all vertices such that, so there is a chain from, say, all vertices may be V, such that there is a chain from A to V with, so the flow at each forward edge smaller than the capacity for forward edges, and f of E positive for backward edges. Okay, so so P is non-empty, so observation, P contains A. By our assumption, P complement contains the sink, because we know there are no augmenting paths from A to Z with this property. So Z would be in the complement. And in general, yeah, P, and so we'll get a cut because every vertex, either there is such a path to it, or there is not such a chain connecting A to it or not. So either every vertex lies either in P or in P complement. Both of them are non-empty, and the first one contains A and the second one contains Z. Okay, so we created a cut, and then there is a small argument here saying that for this cut, so I'll probably have to jump it over a little bit. For this cut, we can check that the conditions of the additional lemma work. That means that if we have an edge from P to P complement, then the flow should be equal to the capacity, or if there is an edge going backward, for this choice of a cut, then the flow should be 0. So there is a small argument, but I'll probably jump over it. Now the last thing is to the last claim is as follows. So if there is an augmenting path, if there is an augmenting path for a flow f in n, then one can increase it. So if we have an augmenting path, then we actually can increase the flow a little bit, and that's why such a flow is not maximal. Okay, and how do we do this? Well, so let us try to think again. What is the definition of the augmenting path? The augmenting path is the path connecting the source and the sink such that along any forward edge, we haven't reached the maximal capacity of the edge, and along any backward edge, we have a positive flow back. Okay, so then we can easily understand by what positive number we can increase our flow. And to do this, we define the following. So so given such a path, such an augmented path, define delta sub p, path p. Define delta sub p as the minimum over all edges, delta e. So e belongs to our path, where delta e is defined as if we have a forward edge, we just take the capacity of the edge minus the flow. This is a positive number by the definition of augmented path. And oops, if this is how to get this back away, yeah. And if it's a backward edge, we're just taking the value of the flow itself, which is again positive by definition. Okay, and so for each edge, we're getting those positive numbers delta, and the minimum over all edges in the path is denoted by delta of the path. And that's again a positive number because we're taking the minimum of a finite number of positive integers, because we assume that, so everything we work over integers, our capacities are integers, or the values of the flow on each edge is an integer. Okay, finally, so here is what we do with our existing flow. So define G of E for each edge along the path. So we'll be not altering any other edges which are not in the augmenting path. But for along the path, we will be adding delta P to each forward edge. And we'll be subtracting delta P along backward edges. And for the remaining edges would be other edges. We'll not be doing anything. And the claim is claim that now G is a flow with value equal to value of G of F plus delta P. So we're getting a bigger flow. Yeah, and so how to prove it? And the proof is that we just have to check the condition. We have to check the condition that defined in this way. G is again is a flow, and then that its value would be equal to that. We can just check at A. By definition, the value of a flow is the outgoing flow from the source, and again from the source we'll be changing one edge, increasing its outflow by delta. So obviously the whole outflow from the source will be increased by delta P. And now why it's a flow, why defined in this way it's a flow, we have to check that the balancing conditions are satisfied. And all vertices except for the source and the sink. So we look at, we haven't changed any other edge except that those again the path, and again the path. If we are going that way, we increase it by delta, and then if we have an edge along the path going the same direction, we also increase it by delta. So the balancing condition at this vertex here will be still satisfied because we added something to the incoming edge, and we added exactly the same thing to the outgoing edge. So the total balance is preserved. And if this edge goes that way, then we diminish this again. So we added an inflow, increased it by delta P, but this would be also an incoming edge to this vertex, and we removed the same amount from another incoming edge. So the total incoming flow here hasn't changed, and all other edges are still the same. So G still defines the flow. Okay, gosh, so I think I'm more or less done. So these two lemmas, lemmas together will tell us that what happens is that for maximal flow, we should be able to find a cut such that for this cut, the capacity of this cut is exactly the value of the flow. And also for this cut, we are just using fully all the capacities of all edges going from P to P complement. And we are not using any of edges going back. So the values of the flow on all edges going back is 0. And actually, so this can be made into an algorithm. So one can, and it mentioned in your book, I think it even mentioned 2 different algorithms. So one can construct a maximal flow in steps, so to say. So we start with an initial network and not assign flow 0 to all edges. And then we'll be creating augmented paths algorithmically. So we'll be trying to find the path with satisfying these conditions. This can be done algorithmically, fairly simply. And once we did it, we'll be increasing our regional flow by this amount, which this delta P we just discussed. And then we have a new flow. If a new augmented path exists, we can still increase it, and so on and so on. We can do it algorithmically and infinite number of steps, because here for the algorithm, it's important that we are working with integer numbers. If we will be working with positive numbers, an algorithm in principle. There are examples where you can continue to infinity, that the execution, there will be no finite number of steps to do that. But since we're working with integers, this will be a finite, fairly quick algorithm due to those who were the authors of this theorem, Ford and Fulkerson. And they actually were programmers, and they were interested in algorithm, not in proving the theorem, but that's what they did. They did both at the end. Both proved the theorem and created this algorithm, which, starting from a zero flow, produces augmenting paths as soon as this is possible. And finally, if you get a situation where no augmented paths exist, then you know by this result that you have obtained the maximal flow through your network. And let me finally go back and see that the example I have shown you in the beginning was actually the maximal flow. And if you look carefully, you can easily see what the minimal cut is. So I'm going back to the beginning of my notes here. So here was an example of the flow. And if I look at my network, and my network had this situation. I had capacity 5 here at this edge and 6 here at this edge. Now, if I'm going to my flow here and see that if I choose a cut in the following way, let me remove this thing and that thing, where we try to do some cut. And now my new cut would be the following thing. If I cut it like this, so my PC would be just Z, the sink, and my P would be the rest of the vertices. I forgot what the names are. So everything except C. P would be vertices minus Z. So the capacity of this cut is exactly 11. It's just 5 plus 6. If we look at this picture here, the picture showing the original capacities of the graph. So this capacity is 11. We have found a flow with value 11, and this is the maximal possible thing we can do. Because the value of the flow can never exceed the capacity of any cut in the network. And here we have a cut whose capacity is also 11. Okay, so I think I'm done for today. And
the cat don't have to be unique, right? There can be many different cats.
Minimal, you mean cats are a lot of. Yeah, so for
the value of the cat is the same, but there can be lots of different cats that all are the minimal.
Yes, this is true. This minimal cut is not uniquely defined. Absolutely, it can be typically for a generically taken network. It's probably unique, but in general you can have several, of course. Yes, but the value should be the same. Yes. Mm-hmm. It's probably the most difficult result in your course, but it's still fairly straightforward and intuitive. And I think it's typically on the exam, you'll have something like this as one of the problems. So you have to pay a little attention to this material. But hopefully in a week, we'll go through a couple of such problems. So you'll have some more experience with it. Okay, thank you so much. See you on Thursday then. Bye-bye.